we'll discuss hypothesis testing. The techniques of hypothesis testing can seem odd and confusing, but the most important thing that I want you to take away from this is actually hypothesis testing is pretty straightforward. The complications come from all the formalism that we put on top of it. Those complications are ultimately necessary. I don't want to say they're unnecessary or pointless. Hypothesis testing is very powerful. Some of the power comes from that kind of stilted, unnatural sense. But these are genuine questions that people ask all the time. One example, I heard a couple students in the hallway, one asking the other a question. Well, if there's nothing going on between you, then why is she on your phone so much? That's sort of a basic sort of hypothesis test question right there. If there's nothing there, then why do we observe these things that we observe? One of the basic questions of a hypothesis test, how likely is it that I'm fooled? That I'm imagining there's some pattern there, which is actually not there. We know we've all been fooled by seeing patterns and randomness. People are into astrology because they believe that some random pattern in the sky has some influence on their life. As scientists, we understand that actually the stars are just randomly scattered in what people think look like patterns. Our little ape brains from millions of years of evolution have gotten good at trying to see patterns in the world, even when there's actually nothing there. It's easy for us to get fooled. So we start by asking, well, what would I expect to see if there were nothing there, if there were really no pattern, just randomness? If conventional wisdom were true, if there's really no difference, that's the null hypothesis. We ponder the question, what would I see if that null hypothesis were true? In the example we're doing in the lab, the experiment where I asked you to mess around with dice and then modify them to get 6 to come up more often. The null hypothesis is that the dice is fair and each side has equal probability of coming up. We all know that in real life I might roll a dice and get a 6 for the first time. That's a 1 in 6 chance. I can roll the dice twice in a row and get a 6 both times. I can figure out that's a 1 in 36 chance. It's certainly not impossible. It's not even very unlikely. We could certainly see it if we're playing a game where players roll the dice many times. To start formalized hypothesis testing, I'd want to get a sense, if I rolled dice 20 times, how many times might a 6 come up? Even if the dice were completely fair. If the conventional wisdom were true, if nothing had been done to these dice, that's what we call the null hypothesis, H0. We contrast that with the alternative hypothesis, HA. The likelihood that I'm going to be fooled, that's the p-value. Later we'll talk about problems with people putting too much faith in p-values. But the idea is valid, even if sometimes overdone. Before we look at the evidence, we start with the question, how low does a p-value have to be for me to reject the null hypothesis? How much evidence do I need to make a decision? There are a lot of details. We don't actually accept the alternative hypothesis. Either we do not reject or we reject the null hypothesis. It's the difference between saying, okay, the null hypothesis looks false, there might be some kind of pattern, versus saying, and I know just what that new pattern is. Right? It's intuitive to understand why we'd ask, how much evidence do I need in order to make a decision? To decide I'm not being fooled, there's something there. By convention, and really nothing more, but in so many studies in economics, we use 5%, or sometimes 1%. That gives a boundary. So if the p-value is less than 5%, then people would typically say, we reject the null hypothesis. Then if the p-value is greater than 5%, would say, we do not reject the null hypothesis. Again, not the same as saying we accept the null hypothesis. It may be true, and in fact often is, in case there's some evidence against the null hypothesis, but I'm not 95% certain that I'm not being fooled. I'm not very confident that the null hypothesis is wrong. We often end up in these borderline cases. There's some evidence, but it's not really strong. Sometimes that may be there's just not enough data. If I'm running an experiment, I can do the experiment again, or I can wait till I get some more data. But there are plenty of cases where people say, I just can't be sure yet. Let's take a normal example. Normal. Often we form a hypothesis test about a mean. Although we can take any value of the mean, without loss of generality, we'll often test against the null hypothesis that the mean is 0. Commonly, the null hypothesis is, well, nothing there. We would say the null hypothesis is that the mean is 0, h naught, is the value mu equals 0, versus HA, the alternative hypothesis, mu is not 0. Recognize that we're comparing two very different hypotheses there. The null hypothesis is focused on a point. Mu is exactly, precisely equal to 0. Whereas the alternative hypothesis is mu is something else, anything else. I don't know what else. Those are very different kinds of hypotheses, which should remind you of why we're not saying we accept one or the other. We might be able to reject the claim that mu is 0, but even if it's not 0, we might not have a very good answer for what it actually is. Again, we look at a sample average. Under the null hypothesis, the sample average is distributed normally. There are cases where it's not, but those are weird. The central limit theorem tells us that under pretty broad conditions, the sample mean is going to have a normal distribution, mean mu, standard error, we can estimate from the data. Under the null hypothesis, the mean would have a normal distribution. Now note that for small samples, we have to correct for the fact that we're estimating the standard error. We'll come back to that later, talk about the t-distribution. For now, take it as a decent approximation, particularly in large samples. Sample average is going to have our usual bell-shaped normal distribution around the true value under the null hypothesis. That's part of why the normal distribution is called normal, because it's so common. If I divide my estimate of the mean x bar by its standard error, then that ratio is going to have a standard normal distribution. Under the null hypothesis, it's going to have a mean 0 and a standard error of 1. Now suppose I calculate x bar over the standard error, come up with an answer of 1. Just pick a number. If I then want to ask, is that a big difference? Is 1 a big number? In this null hypothesis formulation, we say that if the true value of mu were actually 0, what is the probability that we could observe a value of 1 or farther from 0? So in the little picture up top there, what is the probability that we're in the purple area of the bell-shaped graph, not in the middle? In calculating these areas, we find the p-value because the p-value is going to be that purple area. That's the probability that I could observe a value as extreme as or even farther. We calculate the area under the curve, and that's why it's very important for statisticians to learn how to do that area calculation. It's one of the basic things that we do again and again. We can set different levels of the test, but a common version would be we reject the null hypothesis of mu equals 0 at the 5% level if the p-value is less than 5%. We look at the area and say that is the same as, once I calculate x bar over the standard error, if that's greater in absolute value than 1.96, then I'm going to reject the null hypothesis that mu is 0. Or do not reject if this ratio, x bar over the standard error, is less than 1.96 in absolute value. That is the same rule as do not reject if x bar is between minus 1.6 and positive 1.96 times the standard error. We often approximate that to twice the standard error because, 1.96 is awful close to 2. That gives us the confidence interval. If the null hypothesis is true, then I'd expect to see certain values of x bar, and if the confidence interval includes 0, then I would not reject the null hypothesis. If the confidence interval does not include 0, then I could reject the null hypothesis. The p-value is the smallest probability that would still reject the null, so you can also calculate that. For example, somebody reports a p-value of 4% for some particular estimation. Maybe I'd say, okay, less than 5, I would reject. Now, again, don't take all this without many complications and subtleties. We'll keep on getting back to those throughout the course. But that's the simple version to start with.